recently we talked about one-port circuits. The input resistance and the Thevenin and Norton equivalent circuits associated to one ports. And in this and the following few lectures, we'll be talking about two-port circuits, or in short, two ports. Okay, and a two-port circuit is, in a sense, a generalization of the one-port circuit. In what sense? Let's see. Okay, so consider an LTI resistor, okay, two-terminal component. R, and the voltage and the current is labeled as such. Okay. Now, IV characteristics of this component come from Ohm's law. Okay, V equals RI. Let's call this equation 1. Now, in this equation, everything is scalar. Okay, so V is a number, it's a scalar. I is another scalar, and R, which is this resistance, either for this resistor, or you can consider this a representation of the one port where R is the input resistance, and R also is a scalar. Okay, this is a constant, and I and V, they're functions of time, possibly. Now, equation 1 that we're all too familiar with has a natural generalization. Okay, it has in the following sense. Again, we write the same equation, but this time the variables mean a little bit different things. Okay? So this I, suppose that it's vector of size n, okay, so it's a vector in Rn, and likewise suppose that this is also vector of the same size in Rn, okay, and then this R, if this equation to make sense, could be either of the two things. It's either a scalar or a matrix. If it's a matrix, then it should be an n by n matrix. And that's the interesting case. Therefore, we'll be considering that n by n matrix. Okay. Now, that's the generalization of one port. This can be called the representation of an n-port circuit. We will not study this generalization, but we will be considering a very important particular case, which is the case where n equals 2. And when n equals 2, that circuit which has such a representation is called the two-port circuit. Okay. So we will be, for the following few hours, we will be interested in case where n equals 2. Okay. And that's such circuits are called two-port circuits, or in short, two ports. Okay. So two ports means we have two pairs of terminals. Okay. For the one pair, we have the associated current and voltage, V1 and I1. For the other pair of terminals, we have another voltage and current, V2 and I2. And then those two pairs are related to one another through some linear function if the circuit is LTI resistive. Okay. So if you want to express that relation where the voltages are on the left hand side and the currents are on the right hand side, and then you have such equation V equals R times I, and this matrix here is called the resistance matrix. Okay. So here is generalization. Okay, this is our circuit, and from this circuit there are 4 wires sticking out. Okay. Now, for the first pair, we do the labeling plus minus V1, then this is the current. Okay, and for the second pair, we do the labeling plus minus V2, this is I2. So this is called a 2-port circuit. It's LTI resistive. Okay, that's what we're gonna be studying, and we will assume that there are no independent sources inside. No independent sources inside. Another thing that we assume is that, note that with 1 port, forget about these 2 wires, by KCL automatically, whatever this current is, then we have the same current in the opposite direction, I1. Okay. Now, when you have 4 wires, it's not guaranteed that this current equals I1. Okay. So what we're gonna do is we're gonna assume that the connections are such that whatever this current is that's entering from this wire, it's the same current is leaving from the bottom wire. And likewise for the second port. If this is I2, then that must be I2. So that's something that's called port condition, and we will always be working under that condition. We will always be making that assumption. Okay. So with 1 port, if you know I1, then you can automatically figure out V1. With 2 ports, if you know I1, you still need an extra piece of information to figure out what V1 is. Okay, and that extra piece of information could either be V2 or I2. And now, for a while, since we're interested in the resistance matrix case, suppose that that piece of information is I2. Therefore, V1 depends not only on I1 but also on I2. Likewise, V2 depends on the pair of currents I1 and I2. Okay. And that dependence is linear, because we're considering LTI resistive circuit. By that we mean the following: V1 equals R1 1I1 plus R12 I2. Okay. Here R11 and R12, they're constants. Therefore V1 equals some constant times I1 plus some other constant times I2. So that's what we mean by a linear relation between V1 and I1 I2 pair. Likewise, V2 depends linearly on the currents I1 and I2. And so we have some constant times I1 plus some other constant times I2. And instead of writing those 2 equations separately, it's usually more beneficial, okay, more advantageous to write it in matrix form. And when you write it as a matrix form, by which we mean consider stack V1 and V2 into a single voltage vector and stack I1 and I2 into a single current vector, and then what we have is that voltage vector is related to the current vector through a 2x2 matrix, and that matrix is called the resistance matrix. Okay, so let's put these 2 equations into a single matrix equation. I1, I2. And this is V1, V2. And if you do that, the parameters here, R11, R12, R21, R22, appear as the entries of your 2x2 resistance matrix, as follows: R11, R12, R21, and R22. Okay. This thing is what we're calling V voltage vector. The other vector is the current vector, not surprisingly. Okay. And here, this matrix we denote it by capital R. And it's called, again, not surprisingly, the resistance matrix. Okay, it's a very natural generalization of this simple first-order case. R is the resistance matrix. Now, the question, of course, is if you want such a representation for your 2-port, given the circuit, how to obtain those parameters, okay? R11, R12, and so on. That is the entries of the resistance matrix. We're going to see that through a couple of examples. Let's begin with the trivial example. Okay. This is the trivial case. Okay. You'll see immediately why we're calling it a trivial case. Consider this two resistors, okay, LTI resistors. This is R1 and this is R2. Now that we have now 4 wires, and you can consider them together as a single circuit, okay? And then that simple circuit has now 4 terminals sticking out of it, and then you can consider it as a 2-port circuit, okay? By the labeling plus minus V1. This is I1. No, this is automatically I1 too because of the special connection. Here, this is V2 and this is I2. Okay? Now, for this very simple 2-port, let's obtain the resistance matrix. So V1 equals R1 times I1, quickly. But now, because we want to consider the resistance matrix, we want an expression for V1 in terms of I1 and I2. But V1 doesn't depend on I2, so that means it's 0 times I2. Okay, no matter what I2 is, V1 will not be affected by that. Then likewise, V2 equals R2 I2. It doesn't depend on I1, so that means here we have 0 times I1 plus R2 I2. And then if you put those 2 equations into matrix form, you obtain a very special type of resistance matrix, that is a diagonal resistance matrix. I1, I2. So then these are R1, 0, 0, R2. And this is your resistance matrix. Now, let's move on to a more interesting example. Here's our second example, which is not as trivial. Find the resistance matrix R for the following 2-port. Plus minus V1 plus minus V2. This is I2. This is I1, and we have 3 LTI resistors with resistances as given, and we have a dependent source plus minus 2I1. So its control variable is the current of the first port. And for this 2-port circuit, let's obtain the resistance matrix. Okay. So here's a solution. To be able to obtain the resistance matrix, what we need is we need to write V1 and V2 in terms of I1 and I2, because I1 and I2 are the variables that appear on the right hand side. And for this particular topology, it's especially easy to do that. Okay, so let's go ahead and write. We have by KVL and Ohm's law, and also KCL too. So we're using basically everything. So V1 equals this voltage equals plus minus this voltage plus minus that voltage. This voltage clearly equals R1 times I1. Okay, and this voltage equals R3 times the current passing through R3 in this direction. And what's the current passing through R3? Here we have I1, here we have I2, therefore by KCL it must be I1 plus I2. Okay, so what we have here is what we really need to obtain the resistance matrix, that is an expression for V1 in terms of I1 and I2. If you like, you can consider I1 and I2 as our formulation variables. Okay, you want to write everything in terms of them. And similarly for V2. Now V2 by KL is a sum of three voltages. Okay, this voltage plus minus, this voltage plus minus, and this voltage plus minus. Okay. Now this voltage equals, okay, so its polarity is minus plus, but now we're going plus minus, therefore it's minus 2I1. Okay. Then we have this voltage, which is R2 times this current, and this current is no other than I2. And finally, we have this voltage plus minus, which is same as here, R3 times the current passing through R3. Now, since we also have now the expression for V2 in terms of the currents, now it's quite easy to put everything in matrix form. So what we have here is V1, V2 equals the resistance matrix 2 by 2 times the impulse, if you will. Okay, that is the currents. Now let's consider the first row. For the first row, we look at the V1 equation. Okay, so here we have R1 I1, and here we have R3 I1. So those are the terms for I1. So R1 plus R3 therefore must be the first entry, or R11 according to our notation. For I2, we have only R3 times I2, therefore the second entry here must be R3. For the second row, we look at the second equation. For I1, okay, we have minus 2 here, and we have an R3 here. Therefore, this entry must be R3 minus 2. How about the next entry? We look at I2. Here we had a term, R2 I2, and here we have another term, R3 I2, R2 plus R3, therefore must be the last entry. And that 2 by 2 matrix is the resistance matrix representing this 2 pole. Now, for this particular example, we really don't need any other approach because it's quite easy to obtain the resistance matrix by just writing the voltage equation. But for some other topologies, the following method could be more useful. Okay, so let's also talk about that. Another approach for obtaining resistance matrix. Okay. Now we're talking about the general case. Okay. So V1 we said equals something times I1 plus something else times I2, and those somethings are the first and second entries of our resistance matrix. Okay. Now suppose that I2 is somehow 0. If I2 is 0, then what's R11? R11 is the ratio of V1 to I1. Okay, so that implies R11 equals V1 over I1, provided that I2 is 0. Okay, or you can consider other case, I1 is 0. If I1 is 0, then R12 is the ratio of V1 to I2. R12 equals V1 over I2, provided that I1 equals 0. Now this is just a trivial mathematical identity that follows from this equation, but it has a nice interpretation for the physical circuit. It means what? It means that when I2 equals 0, okay, the ratio of V1 to I1 gives you R11. And when I2 equals 0 means you let the second port open circuit. You don't connect anything to it, therefore I2 is automatically 0. And when you do not connect anything to it, all you can go to the first port, okay, and measure the current and voltage, or compute the current and voltage, take the ratio, and that gives you R11. Okay, so this means R11 equals the ratio V1 over I1, provided that the second port is open circuit. Okay, that is when I2 equals 0. And likewise, for this thing you can say that R12 equals the ratio V1 over I2 when the first port is open circuit. Okay. Likewise, you can immediately write V2 equals R21 I1 plus R22 I2, and from this equation follows that R21 equals V2 over I1 when I2 equals 0, and R22 equals V2 over I2 when the first port is open circuit. Okay. So let's apply this approach to the previous example and see that we get the same resistive matrix. Okay. So let's apply this approach to the previous example. And the circuit for the previous example is here. So let the second port be open circuit. That is, let I2 equals 0. Okay. Then in that case, the ratio V1 over I1 gives us R11, and ratio V2 over I1 gives us R21. In other words, if you compute these ratios, V1 over I1 and V2 over I1, what you obtain is, you obtain the first column of the resistance matrix. This is the first entry, and that's the bottom entry. And likewise, you go ahead and set I1 equals 0, then compute the ratios V1 over I2 and V2 over I2. And those two entries together, they give you the second column of the resistance matrix. Okay. Now let's compute the first column. That is when I2 equals 0. When I2 equals 0, V1 equals 1. Okay? V1 equals this voltage, R1 I1. Okay? Plus R3 times this current. But now I2 equals 0, therefore, this current is automatically equals to I1. So we have R3 plus I1. That equals R1 plus R3 times I1. Okay, and then if you take the ratio V1 over I1, you obtain R1 plus R3. Okay. And then how about V2? V2 is this voltage plus this voltage plus this voltage plus minus. Now this voltage is minus 2I1. This voltage is R2 times I2, but I2 equals 0. Therefore, there's no voltage drop across the terminals of R2, meaning that that's 0. Okay, and finally we have plus R3 times this current, and we know that this current, because I2 equals 0, is I1 plus R3 I1. That equals R3 minus 2 I1. Hence, the ratio of V2 to I1 is R3 minus 2. Okay? And these two guys together make the first column of the resistance matrix. Now, let's quickly obtain the second column. When I1 equals 0, okay, now considering the case where we let the first port open circuit. So let's compute V1 in terms of I2, and the ratio will give us the first entry of the second column. Okay, so V1 equals what? V1 equals this voltage plus that voltage, but now this voltage equals 0 because I1 equals 0. Okay, there is no voltage drop across R1 in this case. And what's this current? We have 0 current coming from here, I2 is coming from here, therefore it's automatically I2. Hence V1 equals R3 times I2. Okay, and that means R12 equals the ratio V1 over I2, which is R3. And let's also write V2. V2, this voltage equals this voltage plus that voltage. Now, since I1 equals 0, because the first port is open circuited, here 2I1 is also 0. That means there's no voltage drop across the terminals of the dependent source. So V2 therefore must equal this voltage and plus that voltage. So this voltage is R2 times I2, and this is R3 times I2. R2 I2 plus R3 I2, and clearly that gives us the ratio R2 plus R3. Okay. Now combining all these four entries, okay, gathering them in the resistance matrix, what we have here is R11 is R1 plus R3, R12 is R3, R21 is R3 minus 2, and finally R22 is R2 minus R3. No, this is exactly the same resistance matrix that we obtained earlier. Okay, so and that's what we expect. Okay. Now, in this representation, what we did is we expressed V1 and V2, the voltages, in terms of the currents. Now, one may ask, why not express the currents in terms of the voltages? Okay, that's also possible, and sometimes that representation, depending on the situation, may be even more useful than the resistance matrix representation. Now, let's also talk a little bit about the conductance matrix representation. Okay, so that's our next subject. Conductance matrix representation, where the goal is writing the currents as function of voltages, a linear function of voltages. Okay, so we have an LTI resistive circuit with two pairs of terminals. Okay, port 1 and port 2. This is the labeling. Voltage V1 and V2. This is the current I1. Port condition says that this must be the current going in the other direction. Likewise, this is I2 and this must be I2. Okay, well, not must be, but that's what we're assuming. Okay, once that condition is satisfied, then it's meaningful only then to be able to talk about certain representations. Okay. So by conductance matrix, okay, not surprisingly, we're talking about a matrix that we'll call G, matrix G in general, which relates the voltage vector to the current vector. Okay, so this is the conductance matrix. Okay, denoted by G, and the entries are G11, G12, G21, and G22. Okay. Now let's consider once again our previous example for which we obtained the resistance matrix parameters and try to figure out, if possible, the conductance matrix representation also. Okay. So that's our next problem. Example. Okay, find the conductance matrix G. And the two-port is the same as before. Plus minus V1 plus minus V2. This is I2. This is I1, R1, R2, R3, and we have plus minus to I1 independent source. Okay. And we're after I1, I2 equals V1, V2, G11, G12, G21, and G22. Okay. We have to figure out those four numbers, four parameters from this circuit. Okay. But there are many ways that you can obtain the result. Here is one way that you can apply to any situation where you're to find the conductance matrix. Okay. There is the solution. Okay. Now, G11, G21. Okay. Now, this is what? This is the first column of the conductance matrix. Okay. This is our G conductance matrix. Now, what's first column? How can you obtain first column? Okay. You can obtain first column, but I'm talking about by multiplying with a vector. You can obtain first column by multiplying G by the special vector, where the first entry is 1 and the second entry is 0. That is, G times 1, 0 vector gives you another vector, and that vector is no other than the first column of the conductance matrix of G. Okay. So that is G times 1, 0. Okay. Now let's interpret this mathematical implication, a simple mathematical implication of this equation in terms of our circuit. Okay. So this equals what? If you set the voltages at the ports to 1 and 0, the first port voltage is 1 volt, the second port voltage is 0, that is, the second port is short-circuited. And then for that situation, if you go ahead and measure the currents I1 and I2, you'll measure something. And that something must equal this matrix times 1, 0, which is the first column. Okay? So whenever the voltage for the first port is 1 volts, let's say, and the second port is short-circuited, for that case, when you measure the currents or compute the currents, that vector that you obtain at the end of the measurement or computation must equal the first column of the G matrix. Okay? So that equals I1, I2, the currents under the condition that when V1, V2 equals 1, 0. Okay. So this means Okay, that is V1 equals 1 volt and V2 equals 0. That means the second port is short circuit, and second port is short circuit. Okay. So let's consider that case. V1 equals 1 volt and V2 equals 0. The second port short circuit. For that case, this is okay. So let me quickly redraw the circuit. This is our first port. This is our second port, R1, R3, R2, plus minus 2I1. Okay, now what we're doing is, so this is I1, and this is I2. What we're doing is, V1 is 1 volt, so we're connecting a 1 volt, if you will, a test source. There is 1 volt, and V2 equals 0. That means what we're doing is, we're short circuiting the second port. Okay, so for this situation where we have just this input, single input, there will be some current and voltage throughout the circuit. Now, you take the first current or compute the first current I1, you do the same thing for I2, okay, and then bring those two currents together in a vector, okay, I1 here, I2 here, and that vector is the first column of your conductance matrix, okay, which directly follows from the definition of conductance matrix. Okay, so let's do that by writing the mesh equations. Here we have this mesh, and here we have the second mesh, where we choose the direction, same as the direction of I2, for simplicity. Okay. So if you write KVL in the first mesh, what we have is, starting from this point, okay, so we're going plus minus, plus minus, plus minus. This voltage plus minus is minus 1 volt, okay, so minus 1 plus R1, I1 plus R3 times the current passing through I3, which is I1 coming from here, I2 coming from there, so it's I1 plus I2. Okay, and that by KVL equals 0. So let's give this equation a number. Equation 1. Let's do the same thing at the second mesh, second loop. We have minus 2I1 and then R2, I2, and this voltage is R3, I1 plus I2. Okay, by KVL, that equals 0. That's our second equation. And then from this equation, what we're going to do is, we're going to obtain I1 and I2. So let's combine 1 and 2 in a matrix equation. If you do that, what we have is something times the unknowns I1 and I2 equals the vector that contains the knowns. Okay, I1, I2 equals the vector of knowns, and then we can compute I1 and I2 in this vector by simply multiplying both sides by the inverse of this matrix here. Now, what's this matrix? Okay, that matrix is a matrix that we're familiar with from the previous example. Let's see what it is. For the first row, we look at the first equation, which is here. What are the coefficients of I1? We have R1, I1 here, and R3, I1 here. Therefore, we have R1, R3. The coefficient of I2 is R3. Okay, and whatever remains, we throw to the other side, and this is the guy that remains. If you throw it to the other side, we have 1 here. For the second row, we look at the second equation. For I1, we have minus 2 here and R3. Okay. And for I2, we have R2 and R3. Okay. And what remains is nothing. So therefore, we have 0 on the right-hand side. Okay. Therefore, G11, G21. The first column of the conductance matrix, which is, we saw, which equals the current vector I1, I2 when the voltage is chosen as such. And when the voltage is chosen as such, then we have this equation concerning I1, I2, and that yields I1, I2 equals that matrix inverse times 1, 0. So let's call this equation. That matrix is R1 plus R3, R3 minus 2, and R2 plus R3. Note that this matrix is no other than the resistance matrix. Okay, now let's quickly consider the second column. Okay. Likewise, G12, G22, the second column, equals the conductance matrix times, this time, the first entry is 0, the second entry is 1. Okay? So that's what you measure for the current under the condition V1, V2 equals 0, 1. That is, the first port is short-circuited, and from the second port we apply 1 volt voltage. That is V2 equals 1 volt, and the second port is short-circuited. Okay, so let's also consider that case. Now we're doing the reverse operation. V1 equals 0 and V2 equals 1 volt. Okay. Not that we don't have to write units whenever that something is 0, because 0 volts, 0 millivolts, 0 kilovolts, they all mean the same thing. Therefore, it's okay not to write unit here. It's not wrong to write unit. 0 volts is perfectly fine. We can do that also. Now, this is the circuit once again. This is our 2 port. Okay, R1, R2, R3, plus minus 2I1. Okay, and then what we're doing is here, this is our I1, and this is our I2. What we're doing here is we connect 1 volt test source at the second port, and for the first port we simply short circuit it. Okay. First mesh, second mesh, let's write KVL quickly. At the first mesh we have this voltage plus that voltage equals 0. So R1, I1 plus R3 times this current, which is I1 coming from here, I2 coming from here, I1 plus I2 equals 0. And for the second port, we have minus 2I1, excuse me. Okay, now we have the voltage source here, so let's start from here. So we have minus 1, and then we have minus 2I1, then we have R2, I2, and finally we have this voltage, which is R3 times I1, 2. Okay, and by KVL that equals 0. So let's also give these equations some numbers, 4 and 5, and through 4 and 5 to obtain the next equation, 4 and 5. Okay, implies what? G1 to G22 equals I1, I2, okay? When this condition is satisfied, and when this condition is satisfied, I1, I2 satisfies this equation, and that equals, again, some matrix times this times 0, 1, and that sum matrix is same as the matrix here, okay? The inverse of the resistance matrix. R1 plus R3, R3 minus 2, and R2 plus R3. Okay, and that be our equation 6. Now, by combining equation 3 and 6, we will now obtain the result. Okay. Let's do that. Finally combine 3 and 6, and we can write G equals G11, G21, G12, G22, okay? And that equals, now, G11, G21, first column equation comes from equation 3, the second column equation comes from equation 6. Note that we can combine those two equations into a single equation. Why? Because the matrix here that appears, the 2 by 2 matrix, is same in both cases. Okay? So R1 plus R3, R3 minus 2, R2 plus R3 inverse. And then we stack this column 1, 0, and the other column 0, 1. Note that when we do that, here a special matrix appears. That special matrix is no other than the identity matrix. Okay? Therefore, we can just ignore it and see that G equals the inverse of this matrix. And this matrix is a resistive matrix. So therefore, the conductance matrix equals the inverse of the resistance matrix when the inverse exists. If the inverse doesn't exist, that means you cannot write down the conductance matrix representation for that particular one point. Okay, but for this example, both resistance matrix and conductance matrix exist. Okay, so that equals finally. Okay, what's the inverse of this matrix? You swap the diagonal terms R2 plus R3, R1 plus R3, negative anti-diagonal terms minus R3 and 2 minus R3, and you divide everything by the determinant over delta. And delta is this times that minus this times that. Minus R3 minus 2. That yields R1, R2 plus R2, R3 plus R3, R1 plus 2R3. So that's the determinant of the resistance matrix. Okay. So we obtain the conductance matrix from a little bit longish way, because we already had the resistance matrix, and if you can invert that resistance matrix, that gives you automatically the conductance matrix. Likewise, if you have the conductance matrix already, by inverting it, you can obtain the resistance matrix representation, if the inverse exists. Okay.